Cognitive Computing, and it's presented by ETH Zurich and IBM in partnership with the New York Academy of Sciences. It's part of the Zurich Meets New York, a festival of Swiss ingenuity, a series of events this week, started on the 16th and finish on Friday. And I know today's events were great. I'm sure it'll continue, and there'll be other opportunities for people to participate. I'm Steve Hamm. I'm a writer and videographer at IBM. For a long time before that, I was a technology journalist, and I am the co-author with John Kelly of Smart Machines, IBM's Watson, and the Era of Cognitive Computing, a book that came out from Columbia University Press late last year that I think you'll be getting when you leave today. So hopefully you'll find that enjoyable, interesting, stimulating. You can participate in social networking, the social networking conversation around this evening's event. Got several hashtags for Twitter, hashtag ETH, hashtag cognitive computing, and hashtag ZHNY, and I guess ZH is Zurich.
No, it's the Confederation Helveticorum, the Swiss name in Latin.
Oh, okay.
Sorry for that.
I never would have guessed that in a million years.
That's why I told you.
Yeah. So Zurich has come to New York, but for IBM, this is a long, almost a love affair. I mean, many years of attraction between IBM and the city of Zurich and the people of Zurich. In 1956, when IBM Research was really getting organized as a real corporate unit, one of the first things that they did was they established a satellite office in Zurich. And the strategy then, as now, is that IBM puts research around the world where there are problems to be solved and great minds to be tapped. And that's, Zurich was I believe it was the first step.
Yes,
okay,
yes.
Yeah. And and IBM, I would say, hit the jackpot with Zurich. I mean, all right. So Ambrose Speiser, a professor at ETH, he was the first director of the lab. And there were that launched decades of collaboration between scientists at IBM Research and scientists and academics at ETH. Wide range of areas, a lot of focus on solid state physics, information security, and nanotechnology, and those have kind of continued through the decades. Most notably, or notably, in 1977, an IBM researcher, Alex Mueller, who got his PhD at ETH, formed a joint study agreement with ETH and brought on board a PhD student to work with him, George Bednorz, I hope I pronounced that correctly. And they worked on solid-state physics, and they performed pioneering work in high-temperature superconductivity, and they won the Pulitzer, not the Pulitzer, the Nobel Pulitzer Prize. That's what I wanted. That's what I wanted as a journalist.
Please. They might have won a Pulitzer as well.
Actually, I got a share of a Pulitzer Prize years ago, but
okay.
we won't tell that story tonight. Nobel Prize for Physics in 1987. Another ETH graduate, Heinrich Rohrer, shared the 1986 Nobel Prize in Physics with a young colleague who'd just come in from a PhD program, Gerd Bennig. And they invented the first scanning tunneling microscope, which, as you may know, helped launch the nanotechnology era. So a long history, and continuing up through today, the relationship is, if anything, tighter than ever. And I think in 2011, the two organizations opened a $90 million US nanotechnology center on the campus of IBM Research, jointly funded and with many, designed around joint programs. And they're doing research into new atomic structures and devices for enhancing information technology. And I'm expecting another Nobel Prize. So.
We too.
Yeah.
Me too.
Yeah, next week.
We now know the price tag for a Nobel Prize.
Now, ETH Zurich has earned a reputation among some as the MIT of Europe. but Lino Guzzella, who's in line to become the president next year, early next year. He has much greater ambitions, I understand. He wants ETH, or ETH, as it's pronounced in German, to stand in no other institution's shadow, and he jokes that he wants it to be known as the ETH of the world. So I think there's a great future there. So it's already quite an international institution. 70% of the faculty are non-Swiss, 2/3 of the PhD candidates non-Swiss. But one of his goals is to make the university even more global, and to reach out, and including to New York, to academic partners, to research partners, to corporate partners. And he can talk more about that. So Lino now serves as the rector of ETH, which is the person in charge of teaching. And he oversees all the teaching, promotes new curricula, learning methods, and teaching tools. And he's also a professor of thermodynamics in the mechanical engineering department. And I'm told his research interests are novel approaches in dynamic systems, Nobel, and control of energy conversion systems. So he clearly has a considerable affection for Zurich. Born there, got his undergraduate degree there, his PhD at ETH, a few little hops out into industry and other places in Switzerland, but then back for a long time. So a long time Zuricher, and seems like he's going to be there for a long time now. So talk a little bit about John Kelly. He's had a remarkable career at IBM. He's a Senior Vice President and the Director of IBM Research. He leads the global research efforts, which is about 3,000 scientists and technicians globally in 12 labs in 10 countries. It is one of the largest, or perhaps the largest, corporate basic research institution in the world. And he also guides IBM's overall technical strategy. And his priorities, the leader of IBM Research, have been to stimulate innovation in key areas of technology aligned with IBM's strategy. And he, you may not know, but one of IBM's core values is to create innovations that matter for IBM in the world. And clearly, watching John work, he's insisting that his people uphold that principle and that aspiration. He's also in charge of worldwide intellectual property efforts, and gives you an opportunity to talk about a remarkable number, which is that IBM has received the top number of U.S. patents for 21 consecutive years. More than 6,800 patents in 2013. I saw a graph recently that showed it kind of like this, and then like, the last 20 years, really, it's been remarkable. So since he joined the company, and he got his current assignment in 2007, so well into his tenure, well into reshaping IBM Research. He's had a wide variety of management and technical positions in the company, including running the microelectronics division. This guy loves silicon, but that doesn't mean he's not trying to replace it.
That's right.
In fact, he's very busy and has people very busy on trying to do that. So he's got his Bachelor of Science degree from Union College, a Master of Science degree in Physics from Rensselaer Polytechnic Institute, a doctorate in Materials Engineering from RPI as well. So for me, it's been a pleasure to work with John. I mean, first as a journalist for several years. I worked at Business Week. I loved innovation. IBM was the most innovative company on the East Coast. It was a natural attraction, and John has always been very welcoming and very open, and always has an interesting story to tell about where we're going next. So it's good to have both these gentlemen here, and I think we're going to have a nice discussion. Let's see. Get my papers in order. We're going to have a Q&A, really a conversation. But first I wanted each of these leaders to talk briefly, make kind of a mini presentation first Lino, I'm sorry, let's see. Yeah, first John, because the reason I want, even though Lino's sitting in the middle, I want John to speak first, because I think it's important to kind of lay out, kind of define cognitive computing briefly, and kind of lay out the aspiration, IBM for itself and for the world. Right? That'll kind of set the foundation for everything else we talk about.
Sure, sure. Well, Steve, again, thanks for moderating this discussion, and Lino, welcome to New York.
Thank you.
And thank you for being such a great partner. Our two institutions go back decades and have created a lot of the key technology for our industry. So welcome to New York, and it's thank you for a great partnership. To sort of set the stage for the discussion, I like to sort of position cognitive computing as not just a new computing system or computing paradigm, but a whole new era of computing. And to put things in perspective, I would say that the first era of computing was around tabulators and counting and adding machines, which were based on mechanical switches, and sort of ended that era with vacuum tubes. But they were just simple calculators, if you will. The second era of computing, which is the one that I don't see anybody old enough here to go back to the first era, but the second era of computing is the one that we all have lived in, which I think of as the programmable era of computing, where we as human beings basically through software and programming instructed systems what to do. And I remember back when I began studying computer science, we were literally moving bits, and every instruction had to be programmed into that machine. And of course, we developed higher level programming languages to put our sense into those computers. And those computers have basically been used as productivity tools for humans, for business, and every computing device, our biggest supercomputers and your iPhone or Galaxy are basically programmable devices. What's changed now, though, is the explosion of data in the world and the rate and pace of change. And to just simplify as an introduction, that rate and pace has outstripped our ability to reprogram these systems. And so we are entering and must enter, I think, a third era of computing, which is as different as the second was from the first. And we've coined this term cognitive because it has attributes that are more like human cognition. These are not systems that are programmed, these are systems that learn. These are not systems that require data to be neatly structured in tables or relational databases. They can deal with highly unstructured data, from tweets to signals coming off sensors. So this is an entirely new regime of computer science. Our first attempt at such a system was the so-called Watson system that, for those of you in the US, will remember the competition on this game show, Jeopardy. But that was not a game show. That was tackling a very difficult problem for a cognitive computer, which is deep question and answering in unrestricted domains around complex language. And that's what we built in that first Watson system. And it's our belief, to sort of wrap up here, that Watson system is to this new era of computing what our System 360 was back in the 60s to the second era. It was the first commercially programmable system that began the era of programmable systems. I believe that history will show that Watson system is the first in this new era of cognitive systems to deal with highly unstructured data and the systems that reason and learn that don't require programming. So that sort of sets the stage, I think, Steve, for what this new era is all about.
And Lino, I wondered if you would talk, kind of put on, keep your academic hat on, and talk about kind of the role of universities in kind of this emergent field.
I'll be glad to do that, but let me just first reciprocate the politeness that John extended to me. For us, the cooperation with IBM has been a success story, And I'm sure it will be a success story also in future. You mentioned it, 4 Nobel Prizes came out of it, but that's just the tip of the iceberg. Right. There are so many fruitful cooperations so far, mainly in the area of hardware, I would like to say, nanotechnology and atomic structures. Not so much in software, and maybe this evening is the birth of extended cooperation also in the software business. I would like to make another couple of general remarks. I have so few opportunities to talk to such an audience, so I misuse them always. It is not a new fact that computer science has a dichotomy, an ever-increasing capacity of hardware, Moore's law, doubling of the computing power every 18 months, more and more storage, cheaper and cheaper prices, and a very slow progress on the software side. You could even say sometimes the software goes in the other direction than in the progress direction, but that's another issue. So for many years now, it has been the software side that was lagging the developments in the hardware side. And it's clear that with the ever-increasing power on the hardware side, with the ever-increasing capabilities of the sensor networks, of the big amount of data that we acquire through all the new social media and many, many other approaches, Internet of Things, many, many keywords I could put up, that this distance, this gap, this chasm between the two is becoming wider and wider. So we need new ideas how we can develop software, essentially, or how software can become more flexible. Cognitive computing, what John explained, learning machines, machine learning is the term that we sometimes use, is of course the way to go out. And we must pursue that way in a very vigorous and very academic also, but also practical way. I would like just to drop a little bit a grain of salt in the discussion. I'm old enough to remember that we had similar ideas in the 90s, in the 80s. At that time we were more ambitious. We didn't call it cognitive computing, we called it artificial intelligence, and I think it was a big error to call it artificial intelligence, because cognitive computing has the modesty of not trying to replicate the human brain. It's not the idea as far as I understand it. I'm not a computer scientist, but as far as I understand it, that's not the idea. And I think this is a very clever approach, to really put it down on earth, making it something that is reasonably expectation management, that is reasonably sized for what is really possible. It is essentially, as far as I understand it, very sophisticated math, statistical methods, combined with a lot of data, big data if you want to call it, a huge amount, an enormous torrent of data that comes into it, and for me, extremely important, also a very big shot of physical or systematic understanding of what we are talking about. So it will never happen, in my belief. I may be wrong. I was so often wrong in my life. But I don't think that we will, the illusion that you can just throw a ton of data onto a very clever algorithm and you have no idea what this data is about and what the field is about that you want to talk about, that this will produce meaningful results. So we still will need physicists, medical doctors, biologists, you name it, to understand the field, to define the models, always formalized in mathematical descriptions, and combine these 3 ways. Powerful software and hardware, a lot of data that comes into the picture, and better understanding of the physical world, or whatever the subject is that you want to deal with. And if these 3 things come together, then I'm really excited that we can do fantastic new things in future. And that, if you term it cognitive computing, that's fine for me. You could also call it ETH computing. And as an academic, I can just tell you that...
you didn't answer my question. But
yeah, sorry. I always try to avoid answering questions that are posed to me. As an academic, I can tell you this is a very challenging problem that has no chance to be solved without a systematic, comprehensive effort to go towards it. And that's what good universities are strong at. That's exactly our business, to have a long breath, to have stamina, and to try to solve a problem in a systematic and comprehensive way. So it's fantastic opportunity for universities.
So have you made the domains related to cognitive computing kind of priority areas for beefing up curricula or beefing up faculty, or is it just something you're beginning to look at?
we do, of course. We have 9 priority areas. As one of these priority areas is data science, and this fits exactly into it. And cognitive computing is rooted on a very good understanding of the basic computer science mathematical methods, and this has been always a priority at ETH. We can come to talk later on the dangers that I see looming in this discussion, and there, for instance, cryptography, data security, things like that will play an important role, and we are very strong in that. Or quantum computing, to make the link back to you guys. If you want to have really secure information transmission channels, quantum transmission seems to be one of the best approaches to do that, and Switzerland is very strong in that.
But I thought quantum computing breaks the code, breaks the encryption.
You can use it for
Go either
both
way,
ways.
right?
Yeah.
So it becomes a battle.
That's
It's
right.
always the same.
Interesting, interesting. Well, you know, you raised some issue about the role of computers and the role of people, I think. We talk about cognitive computers augmenting human intelligence, human capability. John, do you want to talk about that a little bit? Because some people remember, you know, the Turing Test, and they think, oh, it's all about recreating the human intelligence, but that's not the way you see it, right?
Not at all.
Yeah.
Not at all. This, you know, where we've sort of demonstrated these powerful computing systems, we sort of benchmarked them in man versus machine. So back in '97, when we did Deep Blue and beat Gary Kasparov at chess, which was, I think, a major milestone for computer systems, we sort of demonstrated it through a man versus machine. With Jeopardy, it was machine versus 2 superhuman men. I mean, incredible people. But that's not what we're up to here. In fact, we have already seen that man and machine are much better than either one alone. And I guess an example I would give is one of the places we've had Watson since the Jeopardy demonstration was at the Cleveland Clinic in the medical school. And they're particularly interested not in doctor-assisted diagnosis that we're doing with some of the cancer institutions here in the city, but they're particularly interested in how to teach their students. And what we love about that is, at the same time, the students are teaching Watson. And what we're seeing is, and they will tell you, much faster learning of the students. We're seeing much faster learning on Watson, and then we're seeing much better decision-making occurring when it's man and machine. And I would just add, I think Lino hinted at concern with these systems, and I think we are always going to want humans involved when there are moral issues or privacy issues in the final decision making, and healthcare is a fantastic example of that. Where trade-offs beyond just known data and a smart machine need to be made around areas like quality of life and other decisions.
Now, Lino, you made a reference to AI and the overinflated promises of AI. And I think because cognitive computing doesn't seek to replace or match human capabilities directly, it's probably not as difficult, but it seems to me it's one of the most difficult things that computer scientists have ever undertaken. I mean, we talked about how every level of technology, you really need a breakthrough to make all of this happen. So, new eras don't come along, all the time, and one of the reasons is that it's so hard. So what's it going to take to really fulfill the promise that we see now for society?
I mean, it depends what promises you're alluding to. Some promises of cognitive computing are close. I think we will see that in a rather near future with a very high probability. One thing must be mentioned, John, and I know that IBM is always stressing that the capability of human voice recognition and interaction with voice feedback to humans is a key element of this new developments. And I believe we are now close to that point where this really becomes viable. We see first examples. Mm-hmm. And so one part of cognitive computation is that it makes the interface with machines for humans that are maybe not so knowledgeable in this field, much more easier than it used to be up to now. Much safer, much more efficient also. So you get a higher bandwidth in the communication. I think that's close. If not there already, it's close. So what you need there is an incremental change or an incremental progress. And there you need to teach people to do what we already know what to do. But then, of course, there is the big steps that really need breakthroughs, and that's always difficult. The only recipe I know how you can expect or hope for breakthroughs is select the best people, give them the necessary means, and trust them. I don't know of any, and if somebody knows in this room, I would be very interested to know that. I don't know of any secure plan how you can make guaranteed breakthroughs, guaranteed Nobel Prizes. If somebody has that secret, please share it with me, only with me.
Part of it's the freedom to explore.
You need room, you need freedom, you need trust, and you need to be willing to accept failure. If you do not accept failures, you will never have breakthroughs. And it's nerve-wracking, of course, for a person like me who spends maybe millions of dollars in something, and at the end nothing comes out. Okay, but there is a chance if you give this time and this trust and these resources that maybe something comes out. The key point is have the right people in your faculty.
IBM Research, big bets, big challenges. You kind of set these huge hurdles to overcome, but you don't specify, oh, you must do it in this by
never.
this path. So,
yeah, I absolutely agree with Lino. You cannot tell brilliant people exactly what to do or how to do it. They won't do it. So it's picking big challenges that people will work on. I would answer your question, Steve. What will it take for society? I think it's going to take massive collaboration and a massive effort. I think there are many technical breakthroughs in speech, voice, dialogue, new computing devices that I hope ETH and IBM invent in our Richelieu lab. But that's just the start. It's sort of think back to the early days of the second era of computing. I mean, we talk today about programming. Well, when we started that era of computing, there was no computer science. There were no programming languages. We had to invent Fortran. We had to, at our initial lab here at Columbia University, we had to create computer science. We're sort of at that point. We need to create an ecosystem with our university partners to create curricula going forward. We need enterprise partners in healthcare and in different disciplines. Just as in the early days of the second era of computing, we work with banks and airline companies to transform those industries with the System 360. We need to now work with the new healthcare and genomics, like we're doing here in the city. We need to work with the new forms of banking systems that are developing going forward. So we need to work through every area of the ecosystem if we really want to materialize this. This is not a 1 year or 2 year or even 10-year effort. This is something that's going to evolve over 20, 30, 40 years. And it's got to come all the way from the education system through these industries to make this happen.
are there new models for corporate and academic collaboration that are emerging that looks like they'll be a big factor in this? I mean, you have the nanotech.
Well, I would just we're taking some of our best partnerships, like with ETH, and we're just doubling down on them. In areas like nano devices, because we're going to need something beyond the transistor to run the next 20, 30 years, clearly. And I think we'll invent it in that lab in Zurich. But we have partnerships now with a lot of different institutions, because this is no longer a game where I can go back to my lab and build a lab, put a piece of equipment in, and invent the next transistor. The discoveries are going to occur in the data space. And frankly speaking, we don't have the data. So take the example in genomic healthcare, where we're working with the New York Genome Center, just down the street here. They have the data. They have the genomic data. We can go out and get the 23 million publications per year in the area of cancer oncology, but they have the genomic data from patients. And so in the new era of computing, we need to bring these things together. So new partnerships in whole new ways across this industry are required. And it's stressing us at every level, financially, IP.
Yeah, I mean, you look around the world and you look at the stress on corporations to perform at a time of slow growth, tremendous pressures, which you would think would take away from research dollars. Lots of universities, hard pressed, especially government-backed universities. So it seems like there's a lot of creativity that's required.
It needs business opportunities. At the end of the day, if some idea is really promising and there is also an economic benefit visible, people are still willing to invest. But it doesn't help, of course, that the industry, IBM is one of the very few exceptions, but many other industries have pulled out more and more from basic research. I mean, I remember many labs, I don't want to mention the names, that do not exist anymore, that had similar ambitions that you guys have. Yeah. For instance, in the Rührstückung. That doesn't help. It also doesn't help that government, of course, pulls back from research funding, or that you have any weird sort of political games played. I mean, let's face it, research is expensive. Basic research, fundamental research is extremely expensive. And it needs a contract with society and economy. We need to fund it. And the bad thing is, nobody can give you guarantees that it's going to work. But the other guarantee I can give you, if you don't try it, it's for sure not going to work. So if you don't take the risk, you have guaranteed failure. If you take the risk, you have maybe a chance of success. And this needs to be conveyed, this message. Research is expensive, so all of you who are taxpayers in these rooms, don't forget when you pay your taxes, part of it goes to a worthy cause.
Well, it's funny. It almost seems like you need a marketing campaign to
maybe
promote science.
Maybe.
Like that, Maybe it'll start right here between the two of you.
Yes,
start a movement.
You have this is a very important point, the understanding of the value of basic science and of applied or translational, how you want to call it, it's not so important. In society is, in my opinion, maybe I'm a pessimist, it's declining.
Yeah, I would just say that I'm extremely fortunate to work for a company like IBM, which has as its sort of core strategy to innovate and succeed financially based on innovation versus some other model of, say, low-cost producer or commodities or something. So that core strategy of innovating and taking a long-term view, I guess we're 103 years old this year, and we'd like to live to be 200. We're the only one standing from the beginning of the IT era. Those two things, those core values around innovation and long-term view, that's the only thing that keeps us with this investment, of $6 billion a year. Otherwise, we would have gone the way of a lot of our competitors. Through thick and thin, it's been investment.
Now, both of you have talked about healthcare relative to cognitive computing. You've talked about healthcare as being a focus. John, obviously, after Jeopardy, the first target in the real world was oncology, was cancer. We've taken on Jeopardy. That was pretty impressive. Now let's take on a real hard problem. And I think there's been a lot of work on that, and a lot of impressive work by IBM and partners, and a lot left to go. But I mean, it seems like this is going to be a very when you think about decision making, this is something that cognitive computing helps with. So, Lino, what kind of things do you foresee ETH doing in that area?
It is an obvious first field where these new ideas absolutely must be tested for many reasons. One reason is that there is an economic perspective that is very, very interesting. Secondly, I would say, or I should have said firstly, this is an ethical question. We need to help people to stay longer, healthier with aging society, with all the problems that we are facing. Don't forget, I may be wrong, but I read recently that the medical knowledge of humanity is doubled every 5 years. The amount of medical data, the medical procedures available. Can you imagine any doctor keeping up with that? No way, this is simply impossible. So if you want to go to your physician and have a chance to get a diagnosis that is more or less up to date, it's clear that you need to provide some tools. It's not going to be an automatic doctor. That's not the idea. but you need to enhance these people with some tools that can help them to stay up to date, at least in a certain way. And this is exactly where cognitive computing can come in, because it handles big data, it doesn't forget anything, it can make statistical inferences, so it's an ideal field to test in these ideas. And it's not a new field. Machine learning, pattern recognition, you look at mammographs and you try to identify is it a cancer or not a cancer. This is a topic that, for instance, at ETH has been tackled since a long time. And I completely agree with what John said. This is the new model requires, the new problems require more people to work together, more people from very different fields. If you don't have the medical understanding, you can have the best computer algorithm that you want to, you will go nowhere. So you need to work together with clinics, you need to talk with medical school that provide the data, but also the know-how to really implement these things. So you asked what is the new business model. I was not able to reply you immediately, but I would say it is even more so as it was in the past, cross the boundaries. Have a deep foundation in your own boundary, be a fantastic statistician, fantastic computer scientist, fantastic whatever, but then be able to transcend these boundaries. Make the step forward, talk to the other people, and really come together with new ideas.
Sounds like the ivory tower is smashed.
Not a good place to make these allusions here, but the ivory towers have been dragged down, yes.
With that. So, we started a little bit late, but we want to leave some time for questions. That's often where some of the best ideas and exchanges come from. So we have 2 microphones. Why don't, anybody who wants to ask a question, why don't you just go up and line up behind the mics? And that's a tried and true method. And I'll just flip back and forth between one and the other. And we'll start right over here.
Lino, I have the solution for you, but I can't give it just to you. I'm a Swiss German woman. Go figure, a woman. We'll start with healthcare. We need to work on a wellness model and not a disease model. We need to stop worrying about hiring people and scientists and physicians only from Harvard, Yale, Princeton, Dartmouth. We need to get out of the model of worrying about being tenured in university settings, and we need to look to people, and some of them are right here in this room, that have used their own money, pulled out their own credit card, and are polymaths and interdisciplinary. They're brain mappers, they're matrix thinkers, and they're on the very edge of solutions. But you're not going to find them at ETH, you're not going to find them at Stanford and Cornell.
Is there a question?
So, that is your solution.
Okay, let's have a beer
That is your
afterwards.
solution. Because if we stay in the regular model of being constrained by patent ownership and supporting a chemotherapy model rather than a wellness model and the cure for cancer, you'll have it. It's already happening all over the world.
Thank you.
But they're not at your ATH.
Over here.
You both said how you cooperate, but I assume you must be competing when you recruit. So I would like to know, what is the difference for a young PhD graduate? Why would he or she either go to ETH or to IBM? What's the research environment? How do the research environments differ between 2 institutions like you?
You go first.
That's a very good question.
Yeah.
In a sense, we do compete for talent. The type of research we do is obviously very advanced. It's very close to academic research. But I think of it as targeted research. So we pick problem areas and breakthrough areas or grand challenges, and then we ask our researchers to work in those general directed areas. So it's not wide open, come do some nice work and publish. We publish a lot, we obviously patent a lot, but we're trying to find solutions to big problems that we believe if we are successful in that general direction, we'll have products and services that will be very competitive. So it's more directed research, but with very broad guidelines around it.
So what would be the characteristics in a person that you would look for, and on the other side?
We're both looking for the most brilliant people in the world, obviously. I would say that to work in our environment, we have a lot of individual contributors, but working across interdisciplinary teams is a must in our environment, whereas maybe it might be more of a want in academic environment. But the ability to team and the ability and the desire to work on things that obviously have intellectual results, but also have impact on the world are the kind of attributes that we're looking for. Lino? And it's not one or the other. It's very close.
It's not a black and white, but
Yeah.
I like the question because it allows us to elaborate on a couple of things. First of all, competition is not bad. Competition is great. In German, you say, Wettbewerb belebt das Geschäft. Competition makes your business more healthy. Secondly, of course, the competition between IBM Research Center and the ETH is much less pronounced than, for instance, between another university and the ETH, because we don't have the same business models. Competition becomes then difficult when you hunt for the same money. Then, of course, some serious problems come up. But this is why we are so happy to have IBM so close and so willing to cooperate with us. Because essentially we have two different business models, and they are absolutely not overlapping in a sense. So for us, it's a true win-win situation. It would be different, of course, if IBM had to work together with, I don't know, there is nothing else that can be compared to IBM, of course, but I don't know, another hardware company. Or if ETH had to compete with Columbia here in New York. The situation there is more difficult. Let me nevertheless give a small hint where maybe the two characters would differ. In a research lab like at Rüschlikon in IBM, you focus on your research. You have fewer distractions from outside. As academics, you have a wider portfolio. You have to teach. Most of the people should teach. You have maybe a little bit more fundraising issues than you have as in a research lab. You need to do a little bit more management. In a research lab, you can focus really on your project, but you have a complete freedom. So it's a subtle difference, but there are, I would say, some differences that people, if they choose wisely, should know to go in that direction or in this direction. I hope I answered your question a little bit.
I would just add one quick thing, and then I want to go on. If I'm going to lose somebody from IBM Research, I want it to be to an ETH. And then, if necessary, I'll compromise and we'll share the person.
And if I lose somebody to IBM, for me, it's not a loss.
Yeah.
It's our ambassador is in IBM, and we have a fantastic situation. No, everything is in harmony tonight. I'm sorry.
That's fine. Over here.
Thank you. This was a very exciting presentation. I'm Susan Krause, the president and founder of Green Corsair Tech Labs, and my question is to Dr. Kelly. First of all, I want to congratulate IBM on your female president. I think that's really setting the stage for America to see women ascending as CEOs of major science and tech companies. My question is, my company forms very basic collaborative and interdisciplinary partnerships with major academic universities on a global and US level. And we're focusing on nanomedicine, biosensors, and genomics and computational genomics. So what would be your suggestion? I'm also filing for my own patents in nanotechnology that are highly innovative in collaboration with university research partnerships. If we'd like to work with IBM in terms of a designated lab for our company so that our patents would be reserved for industry in terms of mitigating risk, because in the public domain, then you're opening up a lot of competitive risk, what would be your suggestions in terms of forming a collaboration with IBM so that we can work with IBM in a designated lab and funding, et cetera?
Yes, well, first of all, we are also proud of Ginny Rometty, our chairman, president, CEO. She's an incredible leader, I think the quickest way is to just reach out to me with an email. And we have the kind of work you're doing going on in Zurich as well as in our lab in Almaden, California. And then we have computational genomics and biology up in Yorktown, just up the road. So the easiest way is, I always find, just connect the experts in our two organizations, find an area of mutual interest, and then we'll put the agreements in place. But find the area of mutual interest and let them have at it. So just reach out with an email, and I'll connect the right people.
Oh, thank you
Look
so
forward
very
to
much.
it. You're welcome.
And Lino, how should people approach ETH from New York? What's the door?
There are many doors to ETH, of course. The preferred door, or let's say the most efficient door, is person-to-person contact. So a faculty member from University A with a faculty member of ETH, somebody from industry. We have so much information on the web. And that's another difference between a research unit as IBM and a university as ETH. We are, of course, much less hierarchical. We are like a Swiss cheese. There are holes everywhere, and you probably are more like a bottle of beer. You have one defined entry, and that's how it goes. So it's rather easy to get contact with ETH. Send emails to those people you believe are expert in the field, and then they will handle with it. Of course, then once the contact is established, then a machine kicks in to make sure that all the IP rights are protected. But that is a second step. First step is really the idea.
Okay, good. Over here.
Good evening. I'm Daniel Schaufelberger with the newly created ETH alumni organization here in the US and work in the pharmaceutical industry. I have a question for John. When can I get my personal Watson? The reason I'm asking that, tomorrow at 7 I will be on the phone with my team in China, in India, in Switzerland, and a few other countries on this globe. And I have a new team member in India, and I would like somebody to teach that person what my team learned over the past 5 years and how to interact in this global environment without me having to do that.
Well, the first step to achieve that is to get Watson from a discrete system onto a cloud with remote access. And that is occurring as we speak. In fact, now the only way you can access Watson is through a cloud access. I will not sell you a Watson system. I'll sell you access through the cloud. The second thing is to create these virtual assistants. Dialogue is a big piece of that. But we're literally, as we're speaking, building different applications on Watson to do that. We've also opened up a commercial ecosystem. And you saw that recently we bought a company. Several companies have announced that they're building applications and businesses on top of Watson. So I think we're going to see an explosion in all sorts of virtual assistants and knowledge brokers built on top of Watson over the next 12 to 24 months.
Great. Over here.
Hi, hello, thank you. I'm trying to explain myself as better as possible. It's related to your question, we were hearing here many things about the cascade effects, like the effects in cascade. It's okay? I don't know, yeah. So I'm wondering if you are thinking also in the consequence of this quantum computer in the future. Like, for example, today's all our internet payments goes in primes. In the numbers. So when these computers are able to all of us, how is going to be the system to make a payment secure? And that's just an example of the consequence that this system could bring to all our current corruptions. So that's it.
I wasn't quite understanding. Were you referring to the previous presentation about complex systems?
Yeah, exactly.
Okay.
Like complex systems, and they were talking about effects, cascade effects, like, I don't know, like collapsing traffic. And I think that, I don't know, this kind of computers that are quantums and they are super efficient, and maybe they are able to solve like the system that is based now to payments, like for primes, that
Okay.
I don't know. It makes sense, or I should reframe
You
it?
know, Lino's, he's ready to go.
Okay.
I'm so sorry. I'm the worst person
That's-
to formulate that question.
First of all, that's not true. You formulated it very well. in my understanding, we have to separate these two things. On one side, we have cognitive computing, which is essentially can use any form of hardware computation. It doesn't matter if it is a classical von Neumann machine, if it is a quantum computer, or if it is, I don't know, 100 million Martian somewhere and doing the computation by hand. It just needs hardware that executes, or not executes the classical programs that we were used in the second generation, but is able to do these new algorithms, these machine learning things. On the other hand, you have quantum computing, the promise. We are not yet there as far as I understand. First instances of quantum computers seem to appear. They seem to be faster, but not so much faster as one hoped for that they would be. But this is then a development in the hardware, and essentially the two things are orthogonal to each other. They kind of flip together, they kind of fold over together when you start to think about secure communication, secure channels. And there one promise is to use quantum mechanics, quantum technology to make a communication that is secure, in the sense that quantum physics is very weird. I don't understand it. I'm a mechanical engineer. So what I repeat to you now is what I heard from other people. Quantum effects are very delicate. If you want to eavesdrop, if you want to tap a quantum line, you disturb the process in a way that the process tells the receiver, I have been disturbed. So it's impossible that you mess with a channel, a quantum channel, without making this channel aware that you have been messing with it. And this, of course, is then the ultimate proof. Then the receiver can delete this information, but because he or she knows somebody has tried to catch that message. But essentially, I wouldn't mix up these two things. Cognitive computation can be done very well on von Neumann machines, as far as I understand it.
That's right.
We just need more powerful machines to be smaller and more efficient. And also an energy question, of course, pops up from time to time. We need to make sure that we don't need many new power plants just to run all these cognitive machines, but that's another issue we can talk another evening. Huh? Maybe you want to add something, John?
No, I would just say that it's going to be a while, hopefully not too long, before we have quantum computers. Today, as we understand them, they're only capable of doing a few things extremely fast and extremely well, but they're not general purpose. And we need to learn a lot more. We not only need to build better devices and faster devices, but we also need to understand the properties of them and how do we build more general purpose systems. That's a good decade or more away before the two come back together. I think that's a good way to think about it.
You know, we started a little late. We're running a little over, but I think it's time for maybe one or two more questions. Let's go here. Yes.
We have time.
Yeah, thanks for calling on me. So I'm a person who writes software. I guess I'm in that second generation of people. I'm wondering what the third generation is. It's not just an algorithm or a collection of them. I'm not sure if it's a special way of organizing a whole bunch of algorithms. I'm just trying to get my hands around what cognitive computing is and how I would go about learning it.
Yes, well, if you start with today's cognitive systems, Watson is an example, and you look inside Watson, there's some very low-level programming that's there basically for machine control, and that's about it. And when that's done, we don't touch it. Then what takes over are these learning systems and these learning engines. And if you look inside of Watson, the two most prominent things are massive sets of statistical algorithms. So one answer would be move from being a programmer to a very high-level statistical mathematician, because that's what is inside this system. And then secondly, the second most important attribute is this machine learning. And this is an area that's been around for a while, but is now really, really taking off. I mean, you see companies spending hundreds of millions of dollars to buy 16 guys in the UK who are machine learning experts. That tells you what the value of that is. So if you can come up with new machine learning algorithms, deeper algorithms, better algorithms, that's where the value is going to be. So, and then lastly, I would say connecting the dots of that to the discipline. So if you're at the boundary of genomics and informatics, that is a very sweet spot to position yourself.
May I ask a quick follow-up?
Sure.
Yeah, so I know a little bit about some of the algorithms, some support vector machine here, clustering there. It seems to me that Watson is a little bit more than that. It seems like the beauty might be, or the power might be, in the organization of the algorithms. Is there a field to describe that?
Yes. So architecture inside these systems is built with a structure that you not only can add algorithms, but you can add whole new capabilities. So today, Watson understands very complex natural human language, but Watson is blind. It cannot understand an image. It is being trained, and we are writing new algorithms and new programs for image recognition, feature extraction from images. So adding new capabilities or new senses to Watson or these cognitive systems is also a huge area of interest.
Thanks.
And if you can do that, give me your business card before I leave. Thank you.
That's
May
good.
I add just one
Please,
sentence?
please.
Just maybe this is helpful to you. Go from pattern recognition to feature recognition.
Yes, that's
Hi. I think sort of following up on a similar vein to the previous question, I had something I wanted to ask of Dr. Kelly. There's been a great conversation tonight about human collaboration, and I was interested to hear more of your perspective on, in the model of cognitive computing, what the sort of computational model, in your perspective, is for collaboration between a computer and a person. Do you think it primarily takes place through sort of natural language dialogue, or do you see that as the sort of central programming paradigm, or is it something else?
I think it will always be, because humans are who we are, natural language will always be a very natural way to interact with a system. And right now I would say our natural language dialogue for these systems is probably the most advanced. If I were to show you Watson talking with you in complete sentences, paragraphs, that's a capability we've now created. It's pretty amazing. I think the next frontier, though, is the fastest I/O into the human brain is still through the eyeball. We're still visual animals. We're very visual. And so we have a massive effort. Again, this goes back to the first question. We said, okay, give Watson the ability to see and visually communicate with humans, and we set a research team off to do that. I think the dialogue will be sort of the next killer app or capability, but I think visual recognition and the ability not just to understand what it sees, but present something to you that causes you to instantaneously understand what it's saying. Now the communication is going to go very, very fast.
Absolutely. I mean, I think it seems to me that in order for it to really be a collaboration, both sides sort of have to elevate one another. And so that's where it seems to me that in some ways
Right.
natural language is limited, in that in its sort of fuzziness, for Watson to elevate us, perhaps.
Yes.
Like we have to sort of evolve that model on both sides.
And I'll give you one last thought to send a thought in your head. We now have created algorithms that understand not just what's being said, but why you're saying it. So it has matched complex natural language understanding with psychological data. And so Watson, when we put that module in the system, will understand who you are and what's motivating you and how to speak back to you most effectively.
That's great. Thank you.
Thank you.
You could figure out what Machiavelli really meant. Over here.
Hi, I'm from the City University of New York Medical School, and I've been doing biomedical research for 40 years. And I sympathize with the comment you made that there's been a real explosion in terms of data that's become available. And one of the problems with generating all this data is that a lot of it tends to be incorrect or not reproducible.
That's a very good point.
And in fact, some studies have suggested as much as 40% of published data is incorrect. Now, if you have a computer or machine that tries to generate concepts based on all the published data or facts, it's not going to do a very good job if it tries to
Not true.
incorporate all of the data, because a lot of it is going to be incorrect. So how do you get around that problem without trying to replicate or reproduce every piece of data?
Maybe I can answer the first answer to that. It was on my list. I prepared a very extensive list, and I wanted to talk about exactly that problem. I'm very grateful that you brought it up. I call it the dirty data problem. You're 100% right. There is so much data out there that is completely rubbish, completely wrong. And it would be very dangerous to blindly rely on all the data that is available. So an essential part of whatever we will call cognitive computing, if it has to be successful, will have to have included into it an automated quality assurance system. So you cannot just take one data point or one source and blindly rely on it. You need to have cross-correlation, you need to have algorithms that validate this data with other experiments. This is an essential part of it. Again, a fantastic research project. How do you do that? Because otherwise you end up in believing in long tails that are not there. And you make decisions that can be, for instance, in a medical environment, catastrophic for a person because just of dirty data. So cognitive computing will be a killer app only if will be able to get rid of dirty data, to launder that data.
The way we approach, that's a great question and absolutely the right answer. The way we approached it in Watson was not to try to predetermine what data to trust, because as soon as you start to do that, you introduce bias into the answer as humans. What we did in Watson is we built algorithms that over time would learn what sources to trust and not trust. So it built through these learning engines a whole set of calibration points that said trust this source more than this source, and it became a set of weighting factors. So we were very careful. A lot of previous AI attempts, machine learning, had tried to introduce bias in the beginning, trust this, don't trust that. The trouble is those systems never worked. So we did it through machine learning to trust the sources.
Sir.
Yes, and I've been following what IBM have been doing in the social business space, as in co-creation, and well, you're probably well connected with them. I've been to several conferences. So what do you feel, so for example, this concept of social business being a connected company, as in bring all your stakeholders into co-create with you, how do you think that can be adapted into the research process when it comes to cognitive computing? Yes, from other sectors of IBM as a social business.
Yes, yes. So, navigating complex organizations has always been an issue, and now it's even more difficult because the old hierarchies, even though I'm a bottle of beer, I guess.
Sorry for that.
The old, the old enterprise business hierarchies are just falling apart. And they're falling apart because of social networking, mobile, social business across and outside of our boundaries. We cannot control it anymore. But to me, that's a perfect environment to apply cognitive computing, because I can no longer get structured data on employees or business processes. It's gone. And so we need to search and analyze massive amounts of social networking data to make decisions. Simple example, large telco in India that we work with wanted to improve their business by understanding the networks of people on their phone system to try to improve the stickiness of their service. Impossible for them to do with traditional systems. But by using these algorithms, they could look for patterns of networks in highly unstructured data to look for groups of people that are prone to switch, and then offer them new options for their service where they would stay on the carrier. So this social business is just ripe for cognitive computing.
Actually, what I'm going to suggest, because it's getting late, is we're going to have a little social time after this. So maybe some of the last questions could be asked during that, if that's okay. Because we want to, I think that we want to have a little bit of that. And as a matter of fact, the cognitive computing technology is going to play a role in our social 15 minutes, because one of IBM's cognitive technologies is something called Chef Watson, and it's a system that where a user can put in some ingredients, some suggested ingredients, maybe a geography of the world, maybe a style of cooking, and we'll get back a recipe that will be novel and tasty, based in part on some of the kind of the social and psychological aspects. Now, we've applied it to a drink. And so I'm going to read you what the drink is called. Cognitive Creativity. Not a very creative title for a drink, but let's see. But it has cognac, orange juice, lemon juice, champagne, raspberries, Macintosh apple, and some kind of mix of apple, honey, gin, and ginger. Now, it sounds a little fruity to me, but you know, see how you like it, and maybe it'll take off and it'll become a signature drink for this part of Manhattan.
We're in the early days of cognitive computing.
Yeah. It's still an experiment, right? So thank you very much. Thanks for your attention. Thanks for your very good questions. And thank you, panelists.